This presentation shows an example of using TCI's Scorpio application performing a homing fix function. The homing fix screen presents direction finding measurements in such a way as to simplify the operator's task of finding the location of an unknown emitter using a vehicle-mounted TCI metrics measurement and direction finding system. This page shows the Scorpio application homing fix screen. The vertical bar to the left of the screen is the Scorpio application navigation bar, which an operator uses to select various Scorpio functions, including the homing fix function shown here. To the top left of the homing fix screen is the homing fix control box. On the left side of the control box is a compass rosette which presents direction finding results relative to the vehicle. In this case, it can be seen that the vehicle is driving away from the emitter as the last result taken is toward the rear of the vehicle. The control box also shows the frequency at which the direction finding measurements are being made, as well as the bandwidth being used for the direction finding measurement. In the bottom right of the control box, you can see that the system has been set to automatically make a direction finding measurement every 45 seconds. It is important to note that during the collection of data shown in this presentation, that there was no operator interaction with the system while the vehicle was being driven. Both good and bad direction finding measurements are shown exactly as the system measured them, to give you a real-world example of what to expect when using the system and the tools that are available to mitigate these types of issues. On the main body of the screen, there is a background map displayed. There are several types of map that can be used. For this example, we're using Bing Maps, showing the satellite view, so that we'll be able to see the target transmitter at the end of the homing fix exercise. Note the color bar at the top right of the screen. This shows the scale of signal strength. The operator can change the range of the scale using the mouse. Just below the homing fix control box, you can see a green dot indicating a received signal strength of around -65 dBm, with a direction finding measurement indicating that the target is located towards the northeast. 45 seconds after the measurement was taken in the previous slide, the system automatically made a second measurement. It can be seen that the vehicle has moved along the road to the west, and that the direction finding measurement taken confirms the initial measurement that the emitter is from the east, but there is no intersecting of the measured lines of bearing, therefore there is no fixed point calculated. It can also be seen that the signal strength is a little higher, around -55 dBm. In the control box in the top left of the screen, it can be seen that the emitter is still coming from behind the vehicle. Note that the most recent measurement is shown in yellow, preceding measurements are shown in gray. Again, 45 seconds later, the system has taken another direction finding measurement. This bearing measurement crosses the bearing taken in the preceding measurement, and a fixed point is calculated and presented in both text form, in the top right-hand corner of the screen, and drawn on the map along with an error ellipse. You can see that the error ellipse is quite large. This is because the intersection angle of the two measurements is very acute. Again, note that the signal strength is higher than the initial measurement, but not quite as high as the second measurement. Also note that the emitter still appears to be coming from behind the vehicle. This is the fourth measurement taken. It can now be seen that the second through fourth measurements are coinciding with each other. On the map, it can be seen that the vehicle has taken a left turn, and in the control box, it can be seen that the target emitter is now originating from the left of the vehicle. As noted in the beginning of this presentation, the data being presented here is an example of what to expect when using the system in the real world. The first measurement could be considered to be bad, but like it or not, that is what will happen in the real world. In this case, the first measurement taken was performed with a freeway bridge between the vehicle and the target emitter. Had we known where the target emitter was, we could have forced the system to only take data when there was a clear view of the transmitting antenna, but in this case, that would have defeated the purpose of showing a realistic example. The fifth measurement again is clearly showing a strong indication of the area from which the target emitter is transmitting. With each successive measurement, the error ellipse is getting smaller and smaller. The sixth measurement agrees with the direction to the emitter, but is a little off as compared with the previous measurements. This was actually due to the measurement being taken whilst the vehicle was crossing a freeway, and there were a large number of light poles and traffic lights in this area. The seventh measurement is totally off as compared to all the previous measurements. This is because the measurement was taken whilst the vehicle was next to a large hotel that was located between the vehicle and the target emitter. There are a couple of points that are important to note here. 1. The signal strength indication is blue, around minus 75 dBm, which is significantly lower than the previous measurements, and 2. That the fixed point and the error ellipse have not changed at all as compared to the previous screen. This shows that the system has automatically calculated that the bearing taken in this measurement does not correlate with the previous bearing measurements and has therefore automatically discarded this measurement from calculating the fixed point. The 8th measurement again confirms the direction to the target. As with the previous measurement, the signal strength is relatively low due to buildings between the vehicle and the target emitter, but in this case, as the measurement happened to be taken at the edge of the building, the system was able to determine a good direction to the emitter. This slide shows the 9th through 12th measurements, all taken at 45-second intervals whilst the vehicle was being driven. For this screen, the operator has double-clicked the 7th measurement, the one that was totally off. This has left the signal strength indication on the map, but removes the line of bearing from the screen. Should the operator wish to do so, he may double-click any of the signal strength dots. This will cause the bearing to be removed, or added back, from the screen and to be removed or included from the fixed calculation. This slide shows the same information as shown on the previous slide, but is a zoomed-in view of the fixed point and the target emitter, showing that the emitter is within the error ellipse and very close to the calculated fixed point. To confirm the measurement, we turned the vehicle around and drove the same route, again leaving the system to automatically take direction-finding measurements every 45 seconds. The first measurement shows a good direction to what we now believe to be the target emitter's location. The second measurement confirms the direction but does not provide a fixed point, as there is no intersection between the two bearing measurements. The third measurement confirms the direction to the emitter. It does provide intersection with the previous bearing measurements, but you'll notice that a fixed point has still not been calculated. This is because there are actually two possible fixed points shown on the map, one just left of center for bearing measurements 2 and 3, and one toward the top right of the screen for bearing measurements 1 and 3. Knowing where the emitter is, we would believe that the fixed point toward the top right of the screen is the one to use. But remember that the system does not have prior knowledge. It is just trying to provide the answer based on the data available to it. As emphasized previously, the purpose of this example is to show how the system copes in a real-world situation. The fourth measurement in this series also isn't a particularly good bearing measurement, but it certainly does narrow down the general location of the emitter. Here, the system has used the bearings from the first, third, and fifth measurements, automatically discarding, but keeping for possible future reference, bearings from the second and fourth measurements. Again, the sixth measurement is discarded from the fixed calculation. The fixed point and the error ellipse have not changed from the previous slide. At the end of the route, the homing fixed screen has again located the emitter close to the same area identified in the first run. A zoomed-in view clearly shows that the system has located the emitter with good precision. If there were roads that had allowed us to have driven either to the east or west of the emitter, it would have been possible to have achieved an even smaller error ellipse, closer to an error circle. However, in this case, the location of the emitter is so closely determined that it would be possible to drive to anywhere within the error ellipse and to be able to see the target emitter's transmitting antenna. As previously stated, the purpose of this presentation is to show TCI Scorpio application being used in a real-world scenario to determine the location of an unknown emitter. Both good and what could be considered bad data have been included to show how the system copes with real-world situations. This particular example was taken in an area of mixed urban and rural environments. The target emitter is in a clear rural area, whilst the measurement vehicle was driven in town through an urban setting. Had it been possible to drive the vehicle in an open rural environment, the ability of the system to determine a target location would have appeared to have been much easier. Conversely, had the target been in an urban setting, or if the vehicle had been driven through a denser urban environment, the ability of the system to determine a target location would have appeared to have been much more difficult, in which case an operator's training and operational experience and expertise would have been more of a factor.